about thermal concepts. You have learned quite a bit of this topic when you were in IGCSE, so some parts I will move on very quickly. Okay, so what are the three processes of heat transfer? Can you name all three? That's right, conduction, convection, radiation. Now please go either read your IGCSE textbook or your IB textbook and refresh on these three concepts. I will not be going through them, but you can be tested on them. Now, is this statement true? The temperature in Dubai is twice of Singapore. Do you agree? Most of you will agree, right? Because 40 degrees is twice of 20 degrees. But you need to know that we need to use the absolute temperature scale. Alright, so when it comes to temperature, we cannot use degrees Celsius because that is not an SI unit. So what is 20 degrees Celsius in the Kelvin scale? It will be 293.15 Kelvin. What about 40 degrees? 313.15 Kelvin. Now, is 313.15 two times of 293.15? It's not, right? So, we cannot, if you want to use degrees Celsius, you cannot say temperature is twice. Alright, you need to use in terms of the Kelvin scale. Alright, how do we do the conversion? Temperature in Kelvin will be the temperature in degrees Celsius plus 273. You can say 0.15. Alright, so what will the temperature in degrees Celsius, what will it be? It will be the temperature in Kelvin minus 273.15. Now this equation can be found in your data booklet, so flip to your data booklet now and check. Can you find it? Okay. Now a bit of background. When we have a gas heated in an enclosed space, the pressure will increase. Alright, so if I'm heating up, the pressure will increase. Now if I plot a graph of pressure against temperature, you'll see that, okay, for one gas, if this is the graph that I get, or these are the points that I get, the results I get, I extrapolate it, I will get a graph that looks something like that. Now for a different gas, if I do the experiment, I extrapolate my results, I get this line. For another gas, do the experiment, draw the graph, extrapolate the results, or extrapolate the line, you get this. So you can see that the lowest pressure P that can exist is at 0. Okay, so this is the lowest pressure. And therefore, what will the temperature be? Now you notice that regardless of what the gas is, the temperature that at which any gas attains at a pressure of 0 is the same. Alright? And the temperature in degrees Celsius here will be minus 273, about minus 273 degrees Celsius. Alright? So because the lowest pressure that can exist is 0, this is the lowest temperature that can also exist. And we call this temperature the absolute 0. Why absolute 0? Because in the Kelvin scale, this will be called 0 Kelvin. Alright? Now what happens at 0 Kelvin? What happens to your particles at 0 Kelvin? Now all the particles will stop moving. And why will they stop moving? Because they do not have energy. So basically, question is, are we able to get a temperature are we able to ever reach 0 Kelvin? Now so far the lowest temperature that can be detected in the universe is about 3 Kelvins. So how can we reach 0, or is it possible to even reach 0? Now before we answer that question, let's do a bit of a thought exercise, okay? Now if you have water at 10 degrees Celsius, at what temperature must the surrounding be in order for the water to reach 9 degrees Celsius? Can the surrounding be 9 degrees Celsius? Not possible, right? Because if the surrounding is 9 degrees Celsius, then your water is going to be in between 9 to 10 degrees Celsius. But if you want it to reach 9 degrees Celsius, your surrounding must be less than 9 degrees Celsius. So if you want your gas to reach 0 Kelvin, what must the surrounding temperature then be? It must be less than 0 Kelvin. But can we reach a temperature that is less than 0 Kelvin? Not possible. So theoretically, it might be a bit difficult for us to be able to ever achieve 0 Kelvin. Alright? Now, what energy does each particle have? You have learned this in IG. Yes, they have microscopic Ke, or we call it internal Ke. Now this internal Ke is due to the vibration and movement of the particles. And because of that, it results in the temperature of the substance. It also has microscopic potential energy, or we call it internal Pe. Now this internal Pe is due to the intermolecular forces of attraction between the particles. So the further the particles are from each other, the greater the internal Pe. So this results in a phase change. All right, now phase change, I don't know if you have heard of this term before, but it means change of state. All right, so if you go to textbook page 95, you can see this highlighted in your textbook. All right, and internal energy, now the internal energy of the substance will be the addition of the internal Ke plus the internal Pe. Try example 1 out now. Pause over here and try it out. All right, so they tell us that a substance changes from solid phase to gas phase without a change in temperature. Now the minute I see solid to gas, what does this tell me? It changes from solid to gas. It means that there is a change in internal potential energy, right? Not just change, but remember just now I told you that as a state changes from solid to liquid and from liquid to gas, the internal Pe increases. So internal Pe actually is increasing. Now when they tell you without a change in temperature, what does this mean? This tells you that there is no change in internal Ke, because temperature is related to internal Ke, phase change is related to internal Pe. Now the question asks for what is true about the internal energy. What is internal energy? Internal energy is internal Ke plus internal Pe, right? And the question also asks for the total internal potential energy of the substance when this phase change occurs. So based on this, we already know that no change in internal Ke, but the question never talk about internal Ke. So okay, let's talk about internal Pe. Internal Pe increases, so internal Pe of the substance is going to increase. Now since this one has got no change, remains the same, but internal Pe increases, what will happen to your total internal energy? It's going to increase. So the answer will be C. Now of thermodynamics, there are 3 laws that if you go online and Google, most commonly the first 3 laws of thermodynamics will appear. We will not be touching on these 3 laws. The question is, what if I have something, what if we discover something that's even simpler than the first 3 laws? All right, so we name it the 0 law. Now we will be learning about the 0 law of thermodynamics. Now you know that if I have 2 objects and they are in contact with each other and they are in thermal equilibrium. Now thermal equilibrium means there is no net transfer of thermal energy. Alright, so if A and B are in thermal equilibrium and B and C are also in thermal equilibrium, the 0 law of thermodynamics tells us that then A and C are also in thermal equilibrium, even though A and C are not touching each other. Alright, now how do we measure temperature? We use a thermometer, right? Have you seen such thermometers before? What substances do we make use of in such thermometers? Yeah, alcohol or mercury. These are the 2 common substances, right? Now when we use alcohol or mercury, what are we assuming? What are we relying on in order for us to know that, okay, the thermometer, the temperature that's recorded is accurate? You're assuming that there is a linear relationship with temperature. You're assuming that as temperature increases, the alcohol, the mercury will expand, right? And it will expand by a constant amount for every change in temperature. So you need to choose a property of the material to ensure that it is linear. So either we talk about expansion of the liquid, expansion of the solid, or the resistance or the potential difference across the 2 points, and it should increase linearly, something like that. right? There's a linear relationship. Now, what about this? What if I have a substance, or yeah, where it will increase linearly, but after a certain point, it drops. Now, can I use such a substance? Now you check. For at one, at 2 points of the substance there are, or the same point of the substance, okay? So say I talk about the expansion, and if you talk about expansion, it expands to say a certain length, for at this certain length L. Notice that there are two temperatures. So can I use such a material? No. So when we talk about functions, you learn this in math, right? If you have an equation that is a linear relationship, yes, you can use it. All right. But if the mapping is such that it's 1 to 2, then we cannot use such a material. All right. Now, what about this kind of graph? Your property is not linear, right, to the temperature, to the change in temperature, but you still can, because of one value of the property gives us one value of temperature. The only problem with using such a thermometer is that you have to calibrate for every single value of the property to its temperature. So you cannot really make a prediction if we use this kind of property or this kind of material, which is why we seldom use such materials. Okay, so we normally use something that will has a linear relationship. And when you have a graph that looks like this, how do we find temperature theta? You also did this in IGCSE, right? You need to use ratio and proportion. Okay, if you're not sure how to do it, please come and look for me for support. Now about water. Why don't we use water in our thermometers? Why don't we use water in our thermometers? We don't, because it doesn't expand linearly. Again, you will have encountered this in IGCSE, and that at 4 degrees Celsius, you know that the volume, okay, so if water is heated, its volume will gradually will increase, right? But then from 0 to 4 degrees Celsius, it doesn't work in the same way, all right? If water is heated, its volume gradually decreases. Sorry, if water is cooled, the volume will decrease until it reaches 4 degrees Celsius. At 4 degrees Celsius, water has the least volume and the maximum density. All right, so this, if you take a look at this, it's quite interesting. At a certain temperature and at a certain pressure, water can exist in all three states: water, liquid, solid, liquid, and gas. This is called the triple point of water. So this is why we don't use water. All right. Now let's move on to thermal energy and specific capacity. So in IGCSE and O levels, you have also encountered this. Turn to your textbook, page 95, and check out your data booklet. Do you see a formula that's given to you? All right, so you have Q equals MC delta theta. We learned this previously. And we know that C stands for specific capacity. Now, if you rearrange the equation Q equals MC delta theta, you get Q over M delta theta. Right, what does this mean? Specific capacity of the substance is the amount of heat energy needed per unit mass per temperature, increase in temperature. All right, so for every 1 kg of substance, for it to increase by 1 degree Celsius or 1 Kelvin, this is the amount of energy needed. So that is our specific capacity. What's the SI unit for specific capacity? You can see this is Q over M delta theta, right? So unit for energy is joules, unit for mass, SI unit for mass is kg, SI unit for temperature is Kelvin. That's why you get joules per kg per Kelvin. Now sometimes you will also see joules per kg per degree Celsius. That's also fine, because for every 1 degree Celsius change in temperature, it is, for every change of 1 degree Celsius, it is the same as the change of 1 Kelvin. So this is something that's very unique over here. In the first few slides, I told you that if you want to talk about temperature, you must use SI unit, right? But for this question here, because we're talking about change in temperature, there is no need for you to convert from degree Celsius to Kelvin or from Kelvin to degree Celsius. Sorry, from degree Celsius to Kelvin. All right, because the change is the same. All right, pause over here and try example 2. So for example 2, they tell us that energy is supplied at a constant rate P. They give us that the gradient of the graph is K and there is a specific capacity C. They ask us for the mass. Now the first thing I do is that, well, energy is supplied at constant rate. When they talk about energy supplied at constant rate P, rate means there is time, right? So actually they're talking about power. This is our power. Alright, so previously what formula did we learn? We learned that Q equals to MC delta theta. But what is Q equals to? Q is energy, right? But this question talks about power. How do I relate power to energy? Q equals to PT. That's right. Now take a look at this graph here. What does the gradient tell me? If I use my rise over my run, the gradient tells us the change in temperature over change in time. Right? Our rise is change in temperature, our run is change in time. So if I were to manipulate this equation here, PT equals to MC delta theta. I bring the T over, I get MC delta theta over T. Notice that delta theta over T, what is this? This is our gradient. What's gradient equals to? K. Right? So you get MCK equals to P. Question asks us for mass. So leaving mass on the right hand side, we have P over CK. So answer is A. Now next, example 3. Try this out on your own, then I'll go through it. The question tells us that air has a density of this value. The question is asking for how much heat in joules is needed to raise the temperature of air in this. What does this tell us? This tells us the volume, right? By 5 degrees Celsius. And they gave us specific capacity of air. Alright, now, remember I told you that whenever you do questions, always label. So they gave us density. The question is asking us for how much heat energy. So heat energy is, you can either use E or Q. For this topic, we use Q to represent energy, okay? Then they gave this to us. We know that this is the volume. They gave us the change in temperature, and they gave us specific capacity C. So I've labeled everything. So what do we do? Since we want to find Q, the formula that we use should be Q equals to, before that. Now density goes to mass over volume. You're given density, you're given volume, you want to find the mass, right? So fit everything in, you can find out the mass. So this is the mass of air. Then what do you do next? You use Q equals to MC delta theta. You know what the mass is, you know what C is, you know what delta is. Fit everything in, you get your answer. Now can I leave my answer like this? Notice all our values here are given to 2SF, right? So you need to write it in 2SF, which would be 3. Sorry, is this even 72 times 1050 times 5? Yeah, exact. So it'll be 380,000 joules. You can also write it in standard form, so it'll be 3.8 times 10 to the power of 5 joules. Okay, now we move on to heat capacity. So heat capacity, you have also learned this in IG. We use capital C to represent heat capacity. And it's equals to small m times small c, mass times specific capacity. Now you know that small c is Q over m delta theta. So if I cancel away the m, I get Q over theta. So what's the definition of heat capacity? Based on this formula here, it is the amount of energy needed to raise the substance by 1 degree Celsius. Do I care about the mass? Not really. it's inclusive, they already take into consideration the mass of the object. Alright, so SI unit for heat capacity would be joules per Kelvin. Please highlight this in your textbook and then write this down in your data booklet because it's not given in the data booklet. Alright, now specific latent heat of fusion and vaporization. So again, we have already learned this previously. You know that specific latent heat of fusion, we use small lf to represent it. Small l with subscript f to represent it. Formula is Q over M. What does that mean? Okay, so SI unit first, joules per Kelvin. Okay, and then you learn before that. So what does this mean? This is the amount of energy needed to raise 1 kg of substance, sorry, not raise, to change 1 kg of substance from fusion, from solid to liquid or from liquid to solid. Okay, what about for vaporization? So it's the amount of energy needed to change 1 kg of substance from liquid to gas or from gas to liquid. SI unit is the same, joules per kg. Now, these two equations are used when their phase change. Notice there's no temperature involved, right? So, during phase change, there cannot be any change in temperature. There is no change in temperature when we are changing phase, when we are changing state. And when we are changing temperature, there is no change of state. So, only one change can happen at a time. Either change of state or change in temperature. Okay, so if I want to compare specific heat capacity and specific latent heat, if you look at the formulas, we have two different formulas, of course. Specific capacity talks about change in temperature. Specific latent heat talks about change in state. So since there's a change in temperature, there'll be change in internal KE. Over here, change in state means change in internal PE of the particles. Alright, can you try example 4? Okay, so they ask for the ratio of the ratio of the units, right? So let's talk about specific heat capacity first. Go back. What's the units for specific heat capacity? Okay, too many. It's too troublesome. So what is small c equals to? Q over m delta theta. So it's joules per kg per Kelvin. What about specific latent heat of vaporization? We're talking about LF, right? So it's Q over M. So it's joules per kg. So what is joules per kg per Kelvin divided by joules per kg? Cancel away, you just get Kelvin to the power minus 1. Alright, can you try example 5 and example 6 on your own now? So the question asks for how much thermal energy is absorbed during the process of minus 10 degrees Celsius of ice becoming 110 degrees Celsius of steam. So we know that from ice, there's a change of state to liquid, then there's a change of state to gas, right? Now, how many of you did this? Q equals to MLF plus MLV. Now, this is wrong. What you need to do, remember I told you that there can only be one change at a time. So what I always do is I do this. I will draw it out, okay? So I start with solid, minus 10 degrees of ice. What's the first thing that will change? Does it immediately change state? No. It will have to change to 0 degrees of ice first. So there's a change in temperature. Then only when it's at 0 degrees of ice, then can it change into water, liquid. Right? After that, it will change to 100 degrees in liquid state. Then from 100 degrees of liquid state, then you can change it to 100 degrees of gaseous state. Only one change at time. Over here, notice change in temperature. Over here, change in state. Over here, change in temperature. Over here, change in state. Then finally, it reaches 110 degrees Celsius of steam. So what should it be? It should actually be Q equals to MC delta theta plus MLF plus MC delta theta plus ml V plus mc delta theta. By the way, this C here will be specific capacity of ice. This C here will be specific capacity of water. This C here will be specific capacity of steam. And each of these at different states have got different values. Alright? Okay, example 6. You should have tried it out already. So how do we do this? Now they tell you that a large cube is formed from ice. Each of the cube is 0.75 meters. So I'm going to just draw this out so that I know. 0.75 meters, 0.75 meters, 0.75 meters. Initial temperature of the cube is minus 20 degrees Celsius. They ask us to determine the energy required to melt all of the ice from 20 degrees Celsius to water. Okay, so what do we do? Same thing, draw it out first. So you start off with solid at minus 20 degrees Celsius. What's going to happen? The first change will be change in temperature. So solid ice in at 0 degrees Celsius. Then finally it melts to 0 degrees Celsius. So over here will be change in temperature. So mc delta theta. Over here change in state. So mlf. So how do I find the energy required? Oops. Okay. Okay. So how do we find the energy required? Over here we say is this mc delta theta. Over here is mlf. So the energy required will be mc delta theta plus mlf. So fit the values in. Now they gave us density of ice. So density equals to mass over volume. I want to know what the mass is. So mass equals to density times volume. What's the density? 920 kg per meter cube. What's the volume? 0.75 times 0.75 times 0.75. So what do we get over here? 0.75 cube times 920. The mass will be 788.785 kg. So over here, because this is my intermediate steps, right? So I can include more SF, no problem. Times C, what specific capacity of ice? Because this is during ice. So it'll be 2.1. Now notice over here it's got kilo. Did you remember that? You must times 10 to the power of 3. Okay, then times change in temperature. So what's the change in temperature over here? 20 degrees Celsius, right? So 20. Now remember I told you don't have to convert to Kelvin because the change in temperature is the same whether it's in degrees Celsius or Kelvin. Then plus 788.785 times specific later here of fusion of ice. So it's 330. Now again take note this is kilojoule, so you must times 10 to the power of 3. Alright, so again calculate that out, you will get the answer. Now the next part would be part B, where they ask us to outline the difference between the molecular structure of a solid and a liquid. So this one you also did in IG. What's the difference between solid and liquid? Solid are all closely packed together, vibrating about its fixed position. Liquid, they are not as closely packed, they're able to slide across one another. Right? So for solid, you must mention about strong forces of attraction. So they vibrate about their fixed position. For liquid, the bonds between the molecules can be broken and reformed so that particles are closely packed, are able to slide over one another. Okay, bonds can be broken and reformed. Okay, example 7. Try this out on your own. So again, now I've given you the answer here, right? Did you get this? So again, how to do such questions? Draw it out. You have ice, so that's in solid state. Now 10 kg, and this is at minus 20 degrees Celsius. This is mixed with water. So water, I'm going to draw on top. This is 100 grams. Now 100 grams, I'm going to convert it immediately into kg because I don't like to work with different units. So it'll be 0.1 kg. And this is at 7 degrees Celsius. Now they tell us that these two are mixed together. what's the final temperature? So the first thing is that I don't even know what state they will finally ultimately reach, right? But you can guess, because water is 100 grams, ice is 10 kg. You're using a lot more ice than water. Most likely your water is going to freeze, isn't it? So let's talk about the change, okay? So what's going to happen is that since the final state is going to be solid, I'll still have 10 kg of ice. Now, do not merge the two, water and ice, together, okay? Do it separately. Your 10 kg of ice will remain as 10 kg of solid state, but it will be at a certain temperature X, which I don't know what that temperature is. For your water, you have 0.1 kg of water at 7 degrees Celsius. What's the first change that's going to happen? That's right, change in temperature. So it's going to change to 0 degrees Celsius. After changing temperature, then it can change in state to 0 degrees Celsius of solid. Now, then it's going to reach a certain temperature X, which I don't know what it is. What's happening to our water? Is it gaining heat or is it losing heat? It's losing heat, right? What about ice? Is it gaining or losing heat? It's gaining heat. So by conservation of energy, heat loss by ice is equals to heat gain by water. Now please make sure you show clear workings like this, okay? So the concept that we're making use of right now is conservation of energy. Now what's the heat loss by ice? There is only one change, so it'll be mc delta theta, and this C is specific capacity of ice, equals to, over, if I come to the top over here, this will be mc delta theta, this will be mlf, this is mc delta theta. So it will be mc delta theta, but my C will be specific capacity of water, plus mlf plus mc delta theta, and this C is specific capacity of ice. Now, are our masses all the same? Is this m, are all these m's the same? No, right? This is mass of ice, this is mass of water, so different masses. Okay, so just take note of that. So this will be 10 times specific capacity of ice 2100, change in temperature of ice 20, equals to 0.1. I'm going to take my m out, okay, so that then this would be C of water. What's C of water? 4200. What's the change in temperature? 7 degrees. Plus specific latent heat of fusion, so it will be 3.3 times 10 to the power of 5, plus C of ice. What's C of ice? 2100. What's the change in temperature? Oh, sorry, I said something wrongly. This change in temperature is not 20 degrees. This change in temperature is 20 minus x. It's an unknown temperature because I don't know what x is. Over here will be x because it's just from 0 to x degrees Celsius. Alright? So, go and work this out. Find out what x is. You should be able to get minus 18.1 degrees Celsius. Okay, we are done. Now, please go and watch this video. And this will be the start of our next topic on modeling of gases.